Welcome to the next video in the Systems Programming video series. In this video, we're moving on to Chapter 13 of Dive into Systems, and in this chapter, we're going to discuss operating systems. So the basic idea of an operating system is pretty much right here. It is this layer in between the user or program and the CPU. So if you do something in a program, are you directly communicating with the CPU? No, right? You don't even know really that the CPU is there, right? Most people using a computer don't even really have much of a concept of the CPU. So you're not directly interfacing with the CPU, but the CPU is doing it is responsible for your program running correctly. So how is it doing it? Well, basically the things that you say that you want or that your program requests is mediated through the operating system. It receives those signals and then translates them into things that the CPU can do. So one thing that an operating system does is, let's say that you boot up Windows or Mac or whatever and you're staring at the desktop. Well, you could grab some program and request that it run, right? Double click on it, and the operating system will essentially do what is necessary to get that working. That is going to mean moving certain data into RAM, right from a disk perhaps, initializing registers and so on, and just basically sending commands to the CPU so that the program can run as intended. Another important thing that the operating system does is implements multi-programming, and that is what is needed so that multiple programs will run at the same time. So when you have multiple programs running, what's going on? Does one of your programs have just some consistent request to the CPU and says, compute this? And how is the other program also able to, send requests to the CPU? Well, it has to be that there's a certain amount of resource sharing, and that for a very lightning fast, unnoticeable amount of time, one process gets to make a certain amount of requests and use up resources. And then the operating system gives the other process a certain amount of resources, and it goes over and over in a cycle so fast that you can't tell that this is happening, but it is the way that you get the impression that, or maybe not even the impression, but the reality that multiple programs are running at the same time, so to speak. So that's done by the operating system. Now, this whole concept of a process, right? A process is an abstraction of essentially a sequence of commands that are being performed. And so anyway, it's an abstraction, and it's going to be the main thing that we look at in this video and the next. There's another abstraction that I think takes up the rest of this chapter, but we're not going to get to it because we only need this section and the next in order to get back into assignments and stuff like that, and like getting back to work doing stuff. So we're going to just study processes, but later on we're also going to study another very important operating system abstraction, which is the concept of virtual memory. Now, an operating system involves a lot of stuff like resource management and so on, but the most important core functionality is called the kernel, and often when we talk about the operating system, so we'll say that the operating system does this or that, and what we really mean is the operating system kernel, the core functionality. So when we talk about just the operating system, we're not really thinking about the full operating system, which has a lot of important things, but the most crucial is the kernel. And that's usually what we mean when we say that. Now, how the operating system does things, right? There are particular specific implementations of the things that it does. Those are called mechanisms. I think policies are basically a high-level description of what those mechanisms are doing. So it's kind of abstracting away the exact implementation details and just telling you a high-level description of what it's doing. Now, what are the things that the operating system is allowed to ask the CPU? It can't just say any random thing. There has to be some set of allowable things for the operating system to request of the CPU. And what it is allowed to request is defined by the system call interface. So for instance, if the operating system wanted to ask the CPU for the time of day, there is a named function that allows it to do that, and the entire interface is the collection of all things that the operating system is allowed to request from the CPU. Devices, likewise, have a similar interface, so without going too much into detail about that, I don't think it's that important that we go into detail about that, but it's a similar story. So here the book is describing that there's this process abstraction and this virtual memory abstraction. Both of these are abstractions, right? These are trying to describe things in a conceptual model that is a little bit unconcerned with the hardware details, just because there are so many different kinds of computers implemented in so many different ways, and we would like to describe just a certain set of behaviors that they all share, and so that's the point of these abstractions. Now, one of the important jobs we said already for what an operating system does is it can start up a program. This diagram seems to be describing, say you have some program saved to disk, it's called a.out, and you would like to run it. Well, the operating system handles that. It basically takes the data that is needed for the program and buses it all over into RAM, making it sort of ready for the CPU to be able to call on that data whenever it needs any part of it. But it also creates and initializes a new process, and exactly what that means, certainly we have to wait until we understand the details of these things better in a little bit. So this is still a high-level description, but in some sense, the operating system starts a process for this program. And the next thing that it does is it initializes the CPU state, which is to say that it gets all of its registers and cache ready to start performing the first few steps of the program. And I think that's all there is to say about this diagram. So here I guess we're going to talk about booting, and the main thing I think that we just need to understand here is that when the computer boots up initially, there is some just code that is ready. Even when your computer is turned off, it has some state of the hardware that is essentially code ready to be run as soon as electricity starts flowing through it. And this code is stored in the firmware, which is to say that it is memory, but it is very non-volatile. But in any case, and firmware is like not totally hardware, not totally software, right? That's the whole idea of that. It can be reprogrammed up to a point, but also not up to a point. So anyway, when your computer starts running, this firmware starts running, you may have already heard of BIOS or UEFI, but in any case, what those things do is they run just enough computing, right? They do just enough to get a small part of the operating system working. And once that small part of the operating system is working, running, it takes over and it does the job of loading all the rest of the stuff that is needed for the operating system, getting loaded into disk and so on. But the somewhat useful fact is that BIOS does not run the entire operating system or anything like that. It only gets a small part of the operating system going so that the operating system can pull in, load, and run the rest of the operating system. Now, this whole section seems to be about I/O, interrupt-driven operating systems, which means that basically the operating system can have some processes, it's doing some computing, somehow it has already been set to do some stuff, and yet it can be interrupted. And these interrupts are basically like you press a key on your keyboard. You're interrupting the operating system because it needs to stop and listen to what you're telling it for that split second or whatever. Or it could come from a network interface card, which is essentially your portal to the internet or whatever kind of network that you may be connected to. It can also get system calls. So a lot of these examples so far have been interrupts coming from outside of the computer, but even while the computer is running some program, that program may sometimes need to, in a sense, go beyond the program in a way, right? Which is to say that really it just needs to ask the operating system if it can ask the CPU for something that it needs. So in any case, those are called system calls. And the point is just that it's another way of interrupting the operating system. Basically, the operating system is doing something, and then it hears this interrupt, so it pauses what it's doing, it fills the request, whatever that might have been, delivers on whatever needed that, and then goes back to doing what it was doing before. So that's an interrupt. And so again, it can come from outside, like a keyboard press or the internet or something like that, or it can come from inside, basically from a program that is running and needs to request something. Now, if we want to think about the system calls, right, the acceptable things that can be requested by a program to the CPU, that is defined by the ISA, the instruction set architecture, which we've seen a little bit already. And then here it starts describing this stuff that seems kind of opaque to me. This the operating system associates with each of its system calls a unique ID number. What does that mean? I don't know. This section I find hard to read, and hopefully it'll become clearer as we progress through this. I have maybe 10% understanding of what it's saying, I guess. I don't know. But anyway, and it tries to demonstrate it with this code, but I have no, and it tries to explain what the code is doing, but I find it somewhat unreadable. So I'm just going to hope that by just going forward and just doing stuff, hopefully this stuff will make more sense to me later on. But I think I did skip over something that is worth just noting, just as a point of nomenclature. When a hardware does an interrupt, we just call it an interrupt. But when the software does an interrupt, we often call it a trap. So anyway, there's also this useful distinction between user mode and kernel mode for requests that are sent to the CPU. So when something is in user mode, it generally has come from a program, a user, and those tend to be they should be restricted in the things that they're allowed to do, because they generally are installed by some person that may or may not be all that trustworthy, and so they need to come with some restrictions. Kernel mode has more power, basically, is allowed to do more. So if you want a concrete example, turning your computer off is something that can be done in kernel mode, right? The kernel of the operating system can send that signal, right? You go to your operating system, you click on the power off button, the operating system itself sends the signal to the CPU to power down, basically. And so that's a command that is issued in kernel mode because it's done by your operating system. It would be bad if a program that you're running could issue that command, because then if some nefarious programmer were to write that command, they could really make your computer basically unusable. So that's the important distinction between user mode and kernel mode. And I guess just to say, how does the mode get set? Like you in your day-to-day life as a programmer setting the mode, you generally wouldn't set it. My understanding is that when the data is sent from wherever it is sent over to the CPU, there is a little bit of the data, like a single reserved bit that is coded for a 1 or a 0, depending on whether it is user mode or kernel mode. And so it's really that simple and directly encoded in the signals that the CPU receives, but you're right, and you're not supposed to have power over setting that bit. Other parts of the system set that bit, and it would be bad if you could control that. Now, here the book describes yet another thing that I find somewhat unreadable. It proposes this, how do you switch from user mode to kernel mode within a particular execution process? It shows these two processes, and it says that the switching is accomplished by writing the operating system code to the top of each process. I have no idea how that solves the problem. I find that almost more confusing than if they had said nothing about this at all. So I have no idea how to make sense of that. And also, it kind of doesn't matter, I guess, because they say that, but it's not done that way anymore anyway, because there was an exploit of this system, and now systems do it some other way that causes programs to run slower, but it's now safer against this exploit. But so I just did not manage to understand anything that it was saying here, really. But again, hopefully if we just charge ahead and just do stuff, then maybe it'll make sense later.